So problem 1 on homework 7 is as follows. Use Smith chart to find the distances D and L for a single stub impedance matching of 30 ohms load to Z0 is equals to 50 ohm transmission line. The characteristic impedance of the stub is also 50 ohms. Okay, so now this problem is as shown here. Okay, so we have a characteristic impedance of 50 ohms here, and we have a load of 30 ohms. We have a small section of the transmission line here, which is of length d. We have to find out what that d is, and we also have a parallel stub here connected at the point, and it has a short on one end and it is connected parallelly to the main transmission line. We have to find out what this length is going to be. So this problem can be written in two parts. Okay, so I have divided the problem into two parts. One is the transmission line added to the load. Okay, so let's call this A. We also have another section which is B, which is basically um, a short and a transmission line of length L added to the main transmission line in parallel. Okay, so let's call this B. Okay, just for simplicity, this is how we are going to attack the problem. Let's say ZL is the impedance. We will talk in terms of admittance. Okay, let's say admittance is YL. Okay, I'm writing small letter YL, which means we have normalized everything. So we have YL and we have Y0. Our goal is to eventually make YL equal to Y0. How do we go about doing it? Let's say YL is the admittance and we add a transmission line with 2YL. Okay, let's say the transmission line admittance is something like this. Okay, let's say it is A plus JB. Don't go into the finer details of the algebra, just try to understand the logic of the problem. So let's say we add an admittance to the load admittance, and by the time we reach point A, we have had a transmission line whose impedance is complex, which is A plus JB. Now we know that YL plus A plus JB is the admittance when you look at it from here. Okay. Now we want to ensure that at this point, that is at the point A, at A, we want Y0 is equals to YL plus A. Why is that true? Because we have 30 ohms here as the load and we have 50 ohms here. So we add some value from the transmission line and make it equal to Y0. Okay, make it equal to 50 ohms. But the problem is we also have another part, which is the JB, which comes with the transmission line, because the transmission line has a complex impedance. So we have A plus JB. So though the real part is actually matching, we also have another impedance, which is basically YL plus A plus J beta. So while this could have been equal to Y0, we still are left with this. How do we remove this one? Now then in comes the section B. If somehow we could make the impedance of this one equal to minus JB, let's say YB is equals to minus JB. Now YA and YB are the same points, so they are connected parallelly. So we could have Y in, looking at it from here. If you look at it from here, it would then be equal to YA plus YB, that is equals to YL plus A plus JB minus JB, that is equals to YL plus A is equals to Y0. Okay, now that means we have to make sure part B has an impedance of JB and part A has an impedance such that when the real part of it is added to YL, we get Y0. So this is a basic approach that we're going to follow to solve this problem. So this is how we're going to attack the problem. Okay, so on the Smith chart, we identify all the different points. So Z is equals to 0 at this end, which means the admittance is equals to infinity. Z is equals to infinity at the right end. That means admittance is equals to 0 here. We've also drawn what is called an admittance circle, which is 1 plus JB. I'll explain more about this as we go further, but for now, let it be there. We'll first find out what the load impedance is once it is normalized. We know that the load impedance normalized is ZL is equals to 30 ohms by 50 ohms, that is equals to 0.6. So let's write the normalized impedance at this point. So this is our load. So let's mark the load impedance and then also find out what the load admittance is, because we have a parallel circuit. It's better to always deal in terms of admittances. Okay, so we have admittance here. So this is ZL is equals to 0.6, which means YL is equals to 0.1667. Let's say 1.67 for now. We will also draw a circle which looks like this. So what we want is, now let's also make some other additions. So because we've drawn YL, let's start a line from the center, draw a line joining the admittance and cutting across the Smith chart to the end. Now, all that we're doing is, if this is our load, we are adding a transmission line of length D, okay, a transmission line of length D, such that the original admittance was 1.67, but we want that admittance to reach 1. Now we know that this circle has an admittance of 1, which is basically 50 ohms. So we will add a transmission line length of D so that we will end up on this 1 plus JB circle. So once we end up on this circle, then that is the length of D, which when added to this load will give us the real part of the impedance to be equal to 1, or real part of the admittance to be equal to 1. Okay, so let's see. So what we do is, then we will join a line through this and write it here. Now, okay, so here at the load end it is 0.25 lambda. Okay, and here it is, we are moving from the load side to the generator side, so we have to read the outermost circle. So that is going to be 0.35 to 3.354, that is about 0.354 lambda. So once we subtract the difference, 0.354 lambda divided by 0.25 lambda, that's going to be 4 lambda. 5 by 5 is equal to 0, 3 minus 2 is equal to 1, so that is equals to, so D is equals to 0.104 lambda. Okay, so this is D, which is, okay, what this means is we are going to add a D which is equals to 0.104 lambda, so that the ZL 30 ohms becomes 50 ohms by the time it comes here. Okay, which is what we saw here. So to get an A which adds up to 50 ohms is a D of 0.104 lambda. But we are also left with some sort of JB. Okay, where is that JB here? So now this point has a JB. How much is that JB is a good question. It's somewhere here, right? So we'll see what it is going to be. It's going to be something like this. It's going to be this line. Okay, now how much is this line? Okay, it's slightly higher than this line. So this is 0.5, this is 0.6, this is 0.55. So it's roughly about 0.54 J, and it is minus 0.54 J. Okay, so we have a minus 0.54 J that is added to the admittance of the line. Now all that we have to do is add a positive 0.54 J. Now where do we find the positive 0.54 J? The positive 5.54 J is somewhere here. Okay, is that correct? Yeah, the positive 0.54 J is somewhere here. So all that we are supposed to do at this point of time is find out how do we add that. Okay, so we have to add a 0.54 J. How do we do that? So we know that when the first transmission line D equals to 0.104 lambda is added to the load, we get the real part equal to y naught. Okay, the real part is equals to y naught, but the imaginary part has a component which is equals to minus 0.54 J. Now we can remove that by adding a plus 0.54 J component, so that uh, we have just the real part left. How do we do this? By using the parallel stub. Now the parallel stub has a length L and has a short at one end, okay, which is z is equals to 0, and it is added in parallel to the existing circuit. So let's first identify what is z is equals to 0. Okay, we know that z is equals to 0 is here, so let's mark the point here. Okay, so this is z is equals to 0 for the second circuit. Now as shown earlier, we will go ahead and mark this point and convert it into a admittance. How do we do that? We write this, so then this becomes y equals to 0. Okay, this is the inverse of that particular short circuit. Now what do we do here? We are going to find out what length has to be added to this short. Okay, so again, as earlier, we will draw a circle. So we have drawn the circle. So now we have a load which is a short, okay, and we are going to add a length L to that. Okay, and we have to make sure that the length is at this point. So we have to add this length so that we get a load of 0.54 J. Okay, so if we add this entire length from here to here, then that is going to be our L. Okay, so L is then going to be, so one half circle is going to be 0.25 lambda plus 0.08. Okay, so that's 0.08 lambda. So we add the two, so one half of a circle is 0.25 plus an additional 0.08 lambda, that is going to be 8 plus 5 13. 0.2 plus 1 is 0.33 lambda. So L is going to be 0.33 lambda. Okay, so if we add this, we are going to get a positive 0.54 J, and so essentially what we're saying is D is equals to 0.104 lambda, L is equals to 3 lambda. If we add these two stubs, then we will have a matched line with impedance equal to just 50 ohms. Okay, thank you.